The notion of pipelining is an important concept because it actually has a big effect on what you see, how your query executes. So one of the things that we were talking about was that when you have left deep joins, you can use pipelining. Let's try to figure out what that means. So so let's say I have two joins. I have R join S. Let's say I'm going to do block nested loop join for both. And let's say both of them have 101 pages. And let's say this is 500, 800, and 600 pages. Okay. So, for example, we know how to, I hope, estimate the cost of a join like this. So if I'm doing a join between R and S, R is the outer relation, S is the inner relation, and I have 101 blocks. For a block nested loop join, what I will do is I will read as much of R as possible into memory, and then I will do a full pass over S, and then I will read the next amount of R, and I will do another full pass over S. And I will do this until I have more blocks from R to read. So I'm going to read R into 100 blocks at a time. And for each group, I'm going to read all of S completely. So whenever you do block nested loop join, the cost has to do with reading R completely once, and then reading S as many times as it takes to go through R. So how many rounds do I have to read R in? So it has 500 pages, and I can only read 100 at a time, so I have to read it in 5 groups, right? So that means I have to read S 5 times, right? So basically, if you want to write it like this. This is just the cost of this join itself, okay? So now let's see what happens. So let's say that after I do the join, so this is what? 4,500, right? 4,000, yeah, 4,500 pages. Okay. Now, as I'm computing this, right, when this is completely done, I'm going to basically produce the output of this join. But I don't need to actually join it completely. What I can do is I can execute this query as much as it takes to fill in the input buffer for this one, right? So I'm going to basically read, remember this iterator interface I told you about get next? So I'm going to read get next, get next, get next for this top operation until I actually fill out the input buffer for that. So what I want to do is I'm going to, given that this is block nested loop join, I'm going to read 100 pages of R join S tuples. Once that is filled, I'm actually going to read T to one page and then do the join over all tuples of T, and then I'm going to output it. So basically, this is the same exact operation, except now the top join is reading tuples from the join below. So it's not reading it from disk, right? Because when this join operates, it actually is producing tuples that's already in memory. So the output of this is already in memory. I'm going to say that doesn't work. So the output of this is already in memory. And then I'm going to fill this block and then read T. So for the second join, all I care is how many times I need to read T to finish my join, right? Because the tuples are produced in memory, all I need to do is just join with T. Well, how many times I'm going to read T, right? How many passes over T? Well, it depends on the size of the output of this. So what is the size of R join S? Okay. Well, we've learned that there are two ways you can compute that. So first, you can compute the number of tuples. Okay. So let's say number of tuples in R join S. Okay. Well, to be able to do that, I need a bunch of other information. I need tuples of R. I need tuples of S. And then I need the selectivity of this join. So let's put some simple expression here. Let's say R dot A is equal to S dot B. So this is going to be 1 over max of n distinct R dot A or n distinct R S dot B. So this is the number of tuples that I expect in the join. I don't know what these values are, so let's fill in some ideas here. So let's say tuples of R is 2000, tuples of S is 5000, and distinct R dot A is equal to, let's say, 2000, and distinct S dot B is 1000. Okay? I'm making some numbers up so we can use these later. Okay? So if that is the case, size of join is 2000, 5000 divided by 2000, which is 5000 tuples. Okay? But this is not really sufficient because I don't know how many disk pages that I can put these 5000 tuples in, right? So, in the homework, I say, okay, let's have an assumption. So let me put an assumption here. Let's say that a disk page is 1 kilobyte, which I'm going to treat as 1000 bytes, just for simplicity. I understand that that's like we are not educated people, but that's what we're going to do. Okay, so then let's say that the size of a single tuple, R join S tuple, is, let's say, 20 bytes. Okay, I am making things up. So that means that in a single page can store 1000 divided by 20, which is 50 tuples. Okay. So if this is the case, and after join I expect about 5000 tuples, that's going to fit in how many disk pages? This join result is going to fit in how many disk pages? 100, right? So given I have 5000 tuples and I have 50 tuples per page, this is going to be 100 pages. Okay? All right, so now let's go back to our join. So we have now found out that this is actually 100 pages. Okay, through a lot of math. Okay, and to find that join, I actually have to read 4,500 pages. Now, what I can do at this point is I can put this 100 pages that's coming out of this join in the 100 blocks for nested loop join. And then the remaining one block, I can read T only once, right? So I only have to read only one time, so one pass over T. So if I do one pass over T, that means the total cost of the join is 4,500 for the inner join plus 600, which is 5,100 pages. So we had to do a lot of things that we learned, but the whole point of this operation was to kind of see that when you read from this join and fill it in here, there is no additional cost of reading this because tuples are produced in memory and then fed to the next operation. And in fact, what you will do is you will not compute this join completely because you need to only compute this join to find enough to fill 100 pages. Well, in this case, it turns out to be the whole thing. So you have 100 pages, and then you're going to do this join and then output results. Okay? If it turned out that the size of this join was greater than 100, then you would still fill this page with 100 page worth tuples, and then do join and output, and then when you're done with this output, ask this operation to give you more tuples, right? So that's kind of the idea of pipelining. So I'm going to do one more example, okay? This is something that people always have lots of trouble with, but it's useful to understand how that works. And I'm going to do this in two separate ways, but this time I'm not going to do computation of the size of output, okay? So let's do another pipelining, but then see two different ways to do the same thing. So let's say I have, again, the same thing. Okay, and I'm going to do 101 and block nested loop join. Also M101 with block nested loop join. So this is 1,000, this is 2,000, and this is 800. And let's assume that the size of the output is about 300 pages, right? So I am going to disregard what that is, but I'm going to assume that the size of the join is going to take about 300 pages, okay? So what that means is I'm going to compute this join first, which is going to be read R once, and then read S 2,000. How many times? Ten times, 1,000 over 100, right? Because you're reading R into 100 pages, so it's going to take 10 times. So you're going to do this. Go over S 10 times. Then you have 300 pages. So you're going to take these 300 pages, but you cannot fit it all into the next join. So you're going to first read the first 100 pages of the join from the operation below, fill out the pages, and then read over T, and then you're going to read T how many times? So you're going to do passes over T because you cannot fit the join result all in memory, right? So you're going to have to read T how many times? 3 times. Perfect, right? So basically this is the full cost, right? So this is doing the first join, and there is no additional cost of reading the results of that because they are produced in memory. And this is the final join by doing passes over T. And you are able to produce tuples as soon as you start to produce tuples from the top join. And then you basically, once you're done processing the first 100 pages, you tell to the operator below, give me some 100 blocks worth of pages, tuples again. And then you continue. But one of the nice things is that you are able to produce tuples here, even though your operations may not have ended, right? So basically, you can continue to produce tuples even though this inner join, the lower join, is still not finished. Let me try to do the same thing, but in a slightly different way. Okay, so I'm going to keep this one here, but I'm going to write a different way of doing the same thing. Now, this is not needed for your quiz, but I want you to think about how it changes when I have a different operator. Okay? So this is almost the same except, and the size of this is 300 pages. The only difference is that this one is now a sort merge join. Okay? So I'm not going to do block nested loop join, I'm going to do a sort merge join. So this part is the same. I have 1000 plus 2000 times 10, right? So the lower join is the same. I'm doing block nested loop join, it takes the same amount. And then, as I read the tuples, I want to first sort them. So what I'm going to do is I'm going to read 100 tuples from 100 pages worth of tuples from the operator below, sort it, write to disk. Read again another 100 blocks worth, read it, write to disk. And eventually, when all the join results have been produced, I will have written first 300 pages of R join S written for step 1 for this join, okay? And I keep reading that into kind of 101 blocks, so that's going to create 3 sorted groups. Okay, so I'm doing a sort, right? So the sort first step, read in groups, sort and write. But I don't read from disk, I read from the operation below, so there is no cost to read, but there's a cost to write it out. Then I am going to do the same with T. So now I'm going to do read T, sort in groups, and write. So I'm going to read T once and write it once. So I'm going to read 800 plus I'm going to write 800 and I'm going to produce 8 sorted groups. Right? So I have 3 sorted groups here, 8 sorted groups here, and I have still 101 blocks for this. So what I can do is I can read 3 blocks of R join S, 3 blocks of T, and now I can do the sort and the join at the same time, right? Find from S the smallest tuple, find from R find from T the smallest tuple, find from R join S the smallest tuple, see if they join, output. Right? Continue doing this. So I can do the last step. So I can do sort, merge, and join by reading both relations once. So that would be 800 for this one and 300 for that one. So now the total cost of this second join was I had to write 300, then I had to read 300, then I had to read 800, write 800, and read one more time. So this is the additional cost of this join. When I did block nested loop, it was just this, right? So basically, I have an additional 600, so I didn't actually gain anything. I was doing this in the office hours yesterday. In the office hours, it was always better to do the sort merge in the next one. But this is why you have cost-based algorithm, because you're going to look and see which one is better. But my total cost in this case is basically 3,000, and this was how much? However much this was, right? So the total cost is, so this is 20,000, 21,000, and this is 3,000, so 24,000 pages. All right, so you add these two up. Now here's a question for you, okay? So they basically have very similar cost, except this is 600 pages more. But there's a very big difference between these two plans, right? So one is a sort merge, and the other one is a block-nested loop join. Because in this case, I can quickly start to produce tuples as soon as this operation starts to produce tuples. In this one, I cannot produce any tuple because I have to first sort this whole left relation. That means I have to finish processing this, sort it, write it, sort this one, write it, and then start to join, right? So what's going to happen is that this will take a lot longer to produce the first tuple, because you actually have to complete a lot more other things to start producing something. And this can produce much earlier, but for both of them, you also have a cost of producing all the results. So basically, whenever you do query optimization, you get two estimates: the time to get the first tuples, the time to get all the tuples. And sometimes one is better than the other, and it's reversed for the other one. And it depends on what your application is. For example, anytime you go to a website, you run a query, you get search results, page 1, and then with links to the other pages, right? So that means you really don't care to get every single result, right? You care to get the first page. So in that case, you're optimizing for the first results, right? So basically what you want is to quickly give the user some results, and as soon as you get the results, then you can decide whether you want to get more, which this can produce you as on demand, or you want to abort. In that case, you basically tell this query it's finished, and then it will deallocate the memory. If you are really interested in getting all the results, then you optimize whichever is faster, and you use that. And that's a totally different optimization, maybe. Okay. This is going to be more difficult because the sort here is what's called a blocking operator. The sort cannot really give you all the results until you process everything. And there are many operators like that in SQL that are blocking. Sort, distinct, group by, right? So you don't want to use these operators unless you really need them. Okay? So this is an important thing to remember, that when you're optimizing for first results, and if the order is not important, any of these sorts are going to be a blocking operation. So that is what I wanted to kind of mention. I think that this is a good point to stop and have the quiz, but I can answer some questions before I go on. Yes?
Can you clarify how you calculated those numbers for the sort, like the cost numbers?
The sort?
Yeah. You lost me after, I couldn't figure out why only 2,000 was being multiplied by 10, and then I got lost after that.
Sort. Okay. So this side. So let me try to do it with a separate one. Okay. So like if you suppose you have a sort. So let's say you have R join S, and you have in fact 100 blocks here, and this is 800, and this is 2,000. Okay. And I want to do sort merge join. Right? So what sort merge join will do is read R, sort. So first I want to sort R, right? If I was doing the sorting, so think of this as follows. So you want to do sort R, sort S, and then read R and S and join. Okay? This is generally how we see sort merge join. So what's going to happen is you're going to read R and write it once, right? So read, write once. That means your cost is 2,000, 2 times 800. And this is going to basically produce partially sorted groups. So that's going to be 8 sorted groups, because you have 800 divided by 100. You're going to do the same thing for S. So you read and write it once. So total cost is going to be 4 times 2,000. And this is going to produce 2,000 divided by 100, 20 sorted groups. Okay. Now, if you want, now you can continue to fully sort, right? Because you can read 8 groups. You can I have 100 pages. I can read 8 groups. I can sort, read, and write. So basically what I can do is, at this stage, I can read, merge, sort, and write. My total cost will be 2,800, and then I will be done with the sorting of R. Then I can do the same thing because I have 20 sorted groups but 100 blocks, so I can do this read, merge, sort, and write, which would be again 2 times, this is 2 times 2,000, okay? And then, now I have a sorted R and a sorted S. I can read them once and join. So that means I will read 800 pages and 2,000 pages. So ultimately what happened on this set side is that I read and written 4 times and a 5th time here, both relations, right? So this is the same as 5 times 800 plus 2,000 total cost. Okay? So this is what sort, merge, join is, right? But the point is that you would not do it this way because you actually don't need to really do this step at all, right? Basically what I have is I have 8 sorted groups here and 20 sorted groups here. So if I read 1 page from each group here and 1 page from each group here, then all I need to do is find the smallest value here and the smallest value here and check if they join. And if they join, I output. And then I read the next one here and the next one here, and if so, output. And I can now continue doing this. Every time one of the sorted groups is empty, I read the next page from that one. And that means I can actually just use this information here by just reading them once to the join. So in fact, I don't need to do this, and I don't need to do these. I can simply read 1 page from each group, sort, merge, and join. Right here. So I don't need to do any of this. All I need to do is basically read R1s, S1s, and join. So that would be an additional 800 plus 2,000. So in fact, the real cost in this case is 3 times 800 plus 2,000. Okay. So what sort does is sort basically allows you to see things in smaller groups. It brings it down to smaller groups. And now I can do my join by basically looking at only 1 page from each group and using the same exact algorithm. So basically, if you did it like this, it would be not incorrect, but that's not really what happens, right? You can actually do this, so you can actually speed it up. Yes?
You reiterate where you got these 3 from?
Which one?
3 times 800
Yeah, so 3 times is because you read and write once here, right? So this is 2 from here. You read and write once from here, right? So then you read this one more time for the join part, and you read this one more time for the join part. So each relation is read and written 3 times. Read, write, read back, right? But when you're reading back, you're not reading it all at once. You're reading it, pages back. Yeah.
Below, you had 5 times the value of each.
Right, so in that case, it's more the naive approach, right? You say, I'm going to first finish sorting, right? So that means you first read and write, but you still have sorted groups, right? So then you do the full sort. You read again, 1 from each group, you sort, but then you write the sorted relation back because after it's fully sorted, I'm going to do the join, right? So you read, write, now it's fully sorted. Now I'm going to read 1 from each and then sort them, right? So you read, write, and read again. So that's 5 times, right? But you don't need the 5. Yes?
So the actual number of groups matter?
Yes. Right? So If you found out that this was, 100 and this was 20, right? So then 120 you cannot fit in here, right? Because I want to be able to do this, I want to be able to read all the sorted groups and all the sorted groups, one block from each, right? For this one, you need 28 pages, and you have 100 pages, so I can do it.
So that's one. So each sorted group is just one.
Exactly. Yeah.
So if it doesn't fit, do you have to do it another way then?
So, what I would do is if this didn't fit, I would reduce one of them. I don't need to do both of them, right? So like if this was, let's say, 200, so I would do one more pass over this so that now it's 2, now they would fit. Right? So because there's no need to both of them sort of. Yes.
So just put the first page notes that you had at the bottom where we wrote the assumptions for the calculation.
Size calculation?
Yeah, where you had the tuples and distinct or
Certainly. Okay. So basically one of the things, let me do one more example. I know you look so worried. All right, so I will do one more example. Hopefully this will help a little bit more. So let's say tuples, pages. So whenever you see numbers like this, right, it just means that, for example, for R, you have 2,000 divided by 50, 40 tuples per page. And for S, you have 5,200, you have 50, 25 tuples per page. Sometimes I will tell you, okay, let's say that, the size of a single attribute is 10 bytes. Right? I mean, this is a simplification because it will depend what kind it is. And let's say a page is 1K byte. And I'm going to say that is 1,000. Again, like an uneducated person. So let's say that I have something like this. So I have I'm going to do it like this. And I'm going to actually put a projection here. Okay, I don't need this actually. Okay. So let's say this is block nested loop join. And let's say M is 21. Okay. So I'm going to first do a scan, table scan of R. Then I'm going to do this on the fly. Then I'm going to do a block nested loop join of S, something like this, right? So what does that mean? It means read every tuple of R. As you read tuples of R, check if they satisfy this condition. And then if they satisfy this condition, while they're in memory, extract all the attributes except for R.B, and then fill the input of this block nested loop join until it has 20 blocks. Then read S one block at a time and do the join and output. Okay? So obviously you're going to read R once only, right? So that's for sure, right? The outer relation you only read once. So R you're going to read only once. you're going to basically have a cost of 50 pages. That is for sure. Okay? So then, when I read R, I am looking for all tuples where R.A is greater than 10. How many such tuples there are? We said we are going to use about a third, right? So we assume that anytime you have an inequality, it's about a third. And I did not put a number that is divisible by 3, so I'm going to do 3 here. I am too lazy to do anything else. So that means I have 1,000 tuples that will be output from that, right? So basically here, I expect about 1,000 tuples, right? Because we said that the selectivity of this is 1/3. Okay. So now I'm going to take these 1,000 tuples and I'm going to fill them into the input of this guy, right? So now, but these tuples are not R tuples anymore. They are tuples that have only single attribute, R.B. So if you have a single attribute like this, and you have 1,000 bytes, you can fit about 100 tuples per page, right? So basically that means if you have a single attribute, you have 100 tuples per page. Do we understand that? A page is 1,000 bytes, so given only 10 bytes, you can have 100 tuples. So if you have 1,000 tuples here, how many disk pages will it take? So after you do the selection, it's going to take how many pages? 1,000 tuples, 100 tuples per page, so that will actually only take 10 pages. This is 10 pages, I have 21 blocks, so that means I can actually do the join in one pass, because I will fill 10 pages with this relation, and then use the rest for S, so I can read S only once. So that means which was 200 pages. So my total cost is actually 250. Okay, there we go. So this is what I expect you to be able to piece together when you're writing the solutions to the homework. Okay? Yes?
Why are you able to read S only once if S fits in 20 rectangles?
So S doesn't need to fit in, but I can fit this outcome of this in here, right? Because I have 21 pages, but the result of this is exactly 10 pages, right? So if you can read the outer relation only once, right? If it was a little bigger, so if it was, let's say, 10 times that, then this would actually be 100. So that means I actually have to read S 5 times. Yes?
You rounded n to like 20. I'm just curious, like, is there significance to like one more?
So that's just so that we don't do a lot of math, right? So if you have 21, right, you have two relations, right? So you're going to give every block except for one to the outer. So if you have 21, 20 blocks I will use for the outer, and one block for the inner. So if it was 101, I would use 100 for the outer and 1 for the inner, right? So that means if I can read all of the outer into 20 blocks, then I only have to read S one time, right? So what will happen though is since you have 21 and my input outer relation fits in 10, I can read 11 blocks of S at a time. That means maybe I can do more sequential scans and it may be faster, but we are going to disregard that. Sure.
Why did you get 10 pages for 1,000 people?
Because after I project here, so I projected with a single attribute.
Oh, it's 100 per page.
Right, that's the logic here, that there is 100 per page because you have 10 bytes. Okay. I know it is really low level, but I'm trying to torture you. But all right, I know. All right. So, do you want to skip this quiz? Is this too much for you? No. Yes. How am I going to get the results then if you do it? Take-home quiz. Well, how is that going to help you actually see the results? All right, what I will do is I will skip this quiz, but post the answers. So you will build on this. All right, so let's stop here and give a break, and then we'll move on to a new topic.